Okay, as the paper says, example problems, parallel and series resistors. Okay, so let's look at the series first. Remember that the equivalent resistance is equal to R1 plus R2 plus R3 plus whatever it is. Okay, you don't even have to have three. It could be only two of them. All right. You can have an infinite amount though, which I guess it's hard to add up infinity, but you get the point. And then for parallel, 1 over REQ, 1 over R1, 1 over R2, plus 1 over R3, and so on, until you run out of resistors, okay? Now, when we go through these, we're not going to have parallel and series together. Okay, that's for a whole nother situation. We'll have a video on that too. So the first thing we need to see is it series or parallel? It's series. So we're looking at this one up here. Okay, so I'm going to call this R1, R2, and R3. So REQ, you should write out R1, R2, R3, but I already wrote them here. So it's 650 ohm, 350 ohm, and 1,000 ohms. So REQ, we're going to do this in our head. 350 plus 650 is 1,000. So it's 2,000 ohms. Okay. I know we're not used to these values up in the thousands, but that's perfectly fine. Okay. You're going to realize we can have 10,000 ohms depending on the resistor. Okay. How about this one? Total resistance for 10 120 ohm resistors. So it's in series. So we just add up 120 10 times. So that'd be the same as 10 times 120. Oops, I put volts. This, okay? So that would just be 1200 ohms. 1,200 ohms. Okay? Next, number 3, a string of 15 ohm Christmas tree lights are connected in series. So here's the deal about that. If you've ever had Christmas lights and one burns out and they all go out, you know they must be in series. A lot of the Christmas lights I put outside, one will go out and part of the string will go out. Okay? So what we know about that is the part that goes out is in series, but the other part are in parallel. So remember, in parallel, the voltage will go to each section evenly. Okay, so if it's 120 volts, you'd have 120 volts to each resistor. Okay, the nice thing about that is you're not searching through all the lights. You only have a smaller section. Normally, just start wiggling it a bunch and see if it works, but it's still annoying to try to get them to work. But all old Christmas tree ones where if one bulb went, they all went. All right, so a string of 15 ohm Christmas tree lights. One burns out, they all burn out. Calculate the total resistance. Okay, well, you take 50 times 15. All right, that's it. 50 times 15. Okay, because it said what? Series. So we basically have like a resistor. I do that 50 times. We don't need to do that. So 50 times 15, if you really want to do it, 750 ohms total. Okay, so let's get down here to number 4. You have two 180 ohm resistors. So R1 is 180, R2 is 180 ohms. Okay, and they're connected in parallel. We want to find the total resistance. Now, I call it REQ, equivalent resistance. Some people call it the total resistance, the equivalent resistance, whatever. Depends on what book you have or what you like to call it, but it's all the same thing. So 1 over REQ is equal to 1 over 180 plus 1 over 180. Now, I know most of you are going to just use your calculator. Smart thing would be, right, same denominator, it'd be 2 over 180, but let's say you're not going to do that. So 180 inverse button plus 180 inverse button. So that means 1 over 180 equals 0.011. So what that means is REQ 1 over equals 0.011111111, okay? So we have to flip that. So you could just hit your inverse button again, and it would turn into REQ is equal to 90, okay, ohms. Now if we did this, right, it'd be 2 over 180, which would be 1 over 90, and we flip inverse it, which would just be 90. Okay. Next one, parallel. We're going to call this R1, R2, R3, 10, 20, and 100. 1 over REQ, 1 over 10, 1 over 20, 1 over 100. So, now some of you don't like the way I did it the previous way, so I'll do it probably the way you would do it. You would do 1 divided by 10 plus 1 divided by 20 plus 1 divided by 100. Okay? Okay, so we get that. 0.16. Not your final answer. Now you have to inverse it. So we have to flip. The way you would do that is 1 divided by 0.16. Okay, or just 0.16, hit that inverse button, and you get REQ 6.25. I'm not even going to round it to anything. Okay, 6.25 for the total or the equivalent resistance. Now, I think we get the point. Now, we have a whole nother slew here of examples. Okay? But you can work through these yourself if you want to copy them down. Let's read them just real quick. 50 15 ohm Christmas tree lights connected in parallel. One burns out, the rest will stay lit. Here's the crazy thing. That would be a lot of wires, okay, to have 50 lights all in parallel. Okay? A lot of wires, because you'd have to have that wire from the beginning go to each one individually. That'd be kind of difficult. That's why I said most of the time what I've seen is like maybe a third of the lights will go out. So basically you have 3 strings. So let's say you had 9 lights total. 3 would be in parallel. 3 would be in series, 3 in series, 3 in series, and then those would be all parallel to each other. It'd be like a combination circuit. But you can do that, just 1 over 15, 50 times. Pain in the butt, but you can do it. Okay. And actually, it's actually not that bad, because we'd have all the same denominator, and so it'd just be 50 over 15. What would that be? 50 over 15. 3 1/3, and then do the flip on that. So, yeah, 0.3 something. Okay. Next one. See this battery pack of here? Okay. So now we're going from a little bit different. So instead of just having resistors, now all of a sudden we have voltage. So what do we do there? So let me see here. Well, I mean, this goes back to the same problem we did. I'll do one of these, but this goes back to watch the other 2 videos in series and parallel and how you go back through and figure out the currents and all of that stuff. Basically, we have a situation here. What do we got? Is it series? Okay. So we have 2 resistors like this hooked up to some power supply. First one, 100 ohms. Second one, 100 ohms. So first thing we got to do, we got to find the equivalent resistance. So for a series, it'd just be 100 plus 100 is 200 ohms. Okay, so that's pretty easy. And then it says, what is the total current? Okay, so if you look back at the other video, you realize the current through both of these are the same if they're in series. So we just use V equals IR, solve for the current. Our voltage is going to be 1.5. See that volt DC current? So if you watch the video too with the notes, it talks about DC. you can almost ignore it and just go 1.5. It'd be like a 1.5 volt battery, which would be like what, AAA? Okay, a AAA battery or a AA. So 1.5 volts divided by 200. 1.5 divided by 200. And yes, I did punch that into a calculator. Amps. Okay, so you're going to find this being the same for the rest of these. You find the equivalent resistance, and then you just go find the current, okay, using Ohm's law. Right? So there's some quick examples on, oh, where's it at? On finding your equivalent resistance in both parallel and series. Know these. You should never have to look these up. They're the most common thing used with resistors, series and parallel. No matter how complex a system looks, it breaks down into two things. You're going to have some in series and some in parallel, and you're going to have to figure the whole entire problem out.